Hello, welcome to Slice of Physics. I'm going to be talking about Faraday's Law and induced EMF. So, remember that we've been talking about this problem where there's a loop of wire and a conducting metal bar lying across the wire, and there's a magnetic field through this loop. And we move this bar to the right, and that creates a force on the charges in the rod pointing upward. This is the velocity of the bar, and that makes the charges move in this loop. So we're going to talk about how to find the current that is produced in this loop. And Faraday's law is a rule that's going to help us understand how that current is produced. So to do this, we would ordinarily have Ohm's law. We would say that the potential difference equals IR. So we would say that the current through the loop is equal to potential difference over resistance. But in this case, the force that is driving the electrons around the loop is not an electric force, it is a magnetic force. So we don't use the idea of potential difference. Instead, we use a very similar idea, which is EMF. It's EMF. And it stands for something, but what it stands for is not very important. It is actually a little confusing, so I'm just going to call it EMF. And an EMF is like a potential difference, except a potential difference is a type of EMF, but an EMF can also include a magnetic, a kind of potential difference that comes from a magnetic force as well as an electric force. So remember that the potential difference is equal to the change in energy that a particle experiences divided by the charge of that particle. And in this case, that energy change is due to the work done by that force, that magnetic force, and the work is equal to the magnetic force times the length of the bar. So L is the length of the bar. So that tells us the potential difference, but really it's not the potential difference. It's because it's a magnetic force, we call it the EMF. EMF is equal to the magnetic force times the length of the bar divided by the charge, whatever charge is going through the bar. So we know that the magnetic force is equal to the charge times the velocity of the bar times the magnetic field. So that means that the EMF is equal to F, which is QVB, times L divided by Q is equal to V times B times L. So that's the electromotive force. And therefore we can say that the current is equal to the electromotive force divided by the resistance of this bar or the wire, bar and the wire together. Okay. So now we're going to find another expression that will help us find another way of thinking about what produces this EMF. So we know that we found that EMF equals VBL. So one thing to notice is that, so let's try to figure this out in terms of flux. So if you'll remember that the magnetic flux is equal to the magnetic field times the area of the loop times cosine of theta, but in this case the cosine of theta is 1, so it's just because the magnetic field is going directly through the loop, so the flux is just equal to magnetic field times the area. So Faraday's law is going to talk about the rate of change of the flux. How quickly is the flux through the loop changing? Well, the magnetic field is not changing, so that's B, but the area is changing. So how fast is the area changing? Well, the area is equal to the length of the rod times, let's say x, where this is x. Right? So this is L, and this is x, so if I multiply them together, I get the area. So which of these is changing? Well, L is not changing, but x is changing. So the change in area per unit time is equal to L times the change in x per unit time. But delta x delta t is just v, the speed of the bar. So that is equal to lv. So that means that this delta A delta T is equal to LV, which means that the change in flux per unit time is equal to BLV. So isn't that interesting? The change in flux per unit time, how quickly the flux is changing, is exactly equal to the EMF that determines the, similar to the potential difference that helps to determine the current. So Faraday's law relates these two quantities. So what we're left with is Faraday's law. It says that the EMF, which is like the potential difference across the bar, except it comes from the magnetic field rather than from the electric field, EMF is equal to the change in flux per unit time. How fast is the flux changing? And that means that the current is equal to the EMF, which is delta flux over delta time, divided by the resistance. So this way you can calculate the EMF if you know the delta flux over delta time, even if you don't know the even if you can't figure out how to use what the magnetic force will be. So for example, let's suppose I have two loops like this and another one that's like this with a longer bar. And suppose they have the same magnetic field in them. And suppose I were to ask which one, and I'm going to move the two bars at the same speed, v. So suppose I ask you which one is going to have the greater EMF, so that if they had the same resistance, which one would have more current? Well, it seems like this area is growing faster, because when this bar goes from here to here, and this bar goes from here to here, this loop gains this much area, whereas this loop gains more area, this much area. So more area is being added to this loop faster. Let's do another example. Suppose I have two loops. One of them, it looks like this, and one of them looks like this. and suppose that the two bars are the same length. These two bars are the same length, but the shape of the loop is different. Well, we know that if these bars are going at the same speed, then the EMF in each loop will be the same, because when this bar goes to here, it's added this much area, and when this bar goes to here, it adds this much area, which are the same amount of area. So the rest of the shape of the loop doesn't matter for determining the EMF. Okay. So in this video we learned about Faraday's Law, which says that the EMF, which is like delta V, but can be for magnetic fields as well as electric fields, is equal to the change in flux, magnetic flux, per change in time. All right.